Hello everyone, I'm Alba Carretero Cerdán, the early student research number 3. I'm doing my PhD under the supervision of Professor Belén Martín Matute at the Stockholm University. And my second supervisor is Enrique Gómez Bengoa, who is at the University of Basque Country in Spain, where I've been for 9 months in order to do my secondment and where I have learned how to use DFT. And today I'm gonna present one of the projects that I worked during that period. That is the DFT calculations for the metal free isomerization of polyenyl ethers. But first, this project is based on the transformation of allylic substrates into more valuable organic molecules. And what our group wanted is to extend the previous protocol to other conjugated systems. So first, I will do a brief introduction of the previous work. In 2016, our group demonstrated that a simple guanidine base as TBD as catalyst can isomerize allylic alcohols and ethers into the corresponding ketones. Under mild conditions, and a broad scope was obtained. Importantly, in this work, they found that TBD is able to isomerize stereospecifically chiral allylic alcohols and ethers with excellent levels of chirality transfer. The computational studies of this work were performed by Morten Ahlqvist and showed that after the rate-determining deprotonation step, a chiral ion pair is formed. Although both parts of the ion pair are not chiral, this intermediate presents chirality. And after a further solvent optimization, they have found that in order to stabilize the ion pair, solvents that does not stabilize charges gave high chirality transfer. In other words, that the solvent assists the chiral ion pair to get tighter. So then, with these results, our group wanted to try this, to study this metal field protocol in other conjugated systems, like where the TBD will be as a base walk over the conjugated systems. So this project was done by 3 of my co-workers, and for this project I just performed the DFT calculations. But first, I will explain the experimental results that they have done. And this project starts by evaluating the reactivity of conjugated polyenyl alcohols, in which the reaction delivers the product via 1,3 proton shift. As it proceeds as for the isomerization of allylic alcohols, our group wanted to extend or to study other related conjugated systems as the polyenyl ethers, that in this case the reaction delivers the product via 1n proton shift, depending on how long the chain is. And in order to gain a better knowledge of the mechanism operating in the conjugated polyenyl ether system, they perform some deuterium studies. In order to do that, if we start from a compound that is deuterated at carbon 1, the deuterium is transferred to carbon 3 and carbon 5. That suggests that the reaction works either via 2 consecutive 1,3 proton shift or a direct 1,5 proton shift. In order to prove that hypothesis, another compound was deuterated at carbon 3. In this case, the deuterium content was transferred to carbon 5. So that suggests that there is a 1,3 proton shift between carbon 3 and carbon 5. And finally, if we start from a compound deuterated at carbon 5, that deuterium content was kept at that position. So that means that once the deuterium content is transferred to carbon 5, it doesn't get transferred to any other position of the conjugated system. Then, with all this information, we wanted to have a better knowledge of the mechanism operating in this transformation. So we performed the DFT calculations. Using the software Gaussian 16, and all the geometries were optimized using the Minnesota functional and this basis set for all the atoms. Then the energies of the single point calculations have been refined using the same functional and this large basis set in a polarizable continuum solvent model. The computational studies of this work suggest that the reaction starts by the deprotonation at carbon 1 for both conformers that can interconvert easily by the simple rotation of the sigma bond, giving this ion pair intermediate that then can be protonated in 3 different ways. In a reversible way at carbon 1, at carbon 3, or at carbon 5, given the corresponding products. As all the energies involved in the mechanism are very similar, that suggests that the reaction goes under thermodynamic equilibrium. Then the product stability will depend on the energy difference distribution between them. In order to prove that, we have performed a kinetic simulation using the software Copasi. And from that simulation, it was shown that the reaction works till the formation, or the reaction goes till the formation of the most thermodynamically stable product, which is compound number 4, and once it's formed, the reaction stops. And from this kinetic simulation, we also get information about the stereoisomeric ratio between these two products, that it's almost nearly identical to the experimental one. And then, additionally, we have also performed the theoretical calculation of the kinetic isotope effect, which gave a theoretical result of 3.7 and 3.5 kinetic isotope effect, for which is in agreement with the experimental results that they have found with the deuterium labeling studies, that suggest that the rate determinant step is the deprotonation step. Finally, the conclusions of this work are that the reaction pathway follows a 1,3 proton shift or a direct 1n proton shift till the formation of the most thermodynamically stable product. The DFT calculations show that the reaction proceeds under thermodynamic control, and the DFT calculations confirm that the rate determinant step is the deprotonation step. I would like to thank to my supervisor, Professor Belén Martín Matute, for giving me this opportunity, also to Professor Enrique Gómez Bengoa, to my co-workers in this project, to the past and present members of BMM and the group at the University of the Basque Country, and to the fundings that make this possible, and to all of you for your kind attention.